This is the lecture on ordinal measurement. Because this lecture comes at the beginning of the course, there are a number of fundamental concepts we need to consider. These concepts will be used throughout a number of lectures, so that it will be worth spending some time considering them, giving some examples, etc. Let's start with order properties of binary relations. Most of you will know these properties, but it'll be important to review them for reference here. First is transitivity. A relation is said to be transitive on a set A, let us say, if for any elements A, B, and C, if A bears a relation to B and B to C, then A bears a relation to C. Notice that I haven't used a general relation symbol, but what is an intuitive equal to or greater symbol. And we'll be using that throughout for the relations between objects. It, of course, is mirrored on the corresponding relation for equal to or greater among numbers. The second property is connectedness. For any two elements in the set, A and B, A is at least as great as B, or B is at least as great as A. Notice it's convenient, instead of saying equal to or greater, because we also don't want strictly equal, to say at least as great as. What at least as great as means in empirical contexts of measurement will vary from one empirical situation to another. For example, it may mean at least as great in weight, at least as great in height, etc. And sometimes we wouldn't say great, but use some other general adjective. Let's look at some examples of relations that have these two properties of transitivity and connectedness. Well, the familiar numerical example is to take the set of real numbers and to take the ordinary numerical relation of equal to or greater. It's obvious and familiar that that relation is transitive and connected on the set of real numbers. It's important also to consider other examples than numerical ones, the ones that will be ultimately of interest in the case of measurement for empirical purposes. Let us make up a simple one. We might have a set of three individuals. The set A consisting of three individuals, Smith, Jones, and Walker, and we can consider their height. Now, S, that is Smith, is at least as tall as himself. Let's say Smith is taller than Jones, and Smith is taller than Walker. Now, we also say here Jones is at least as tall as Smith. So when I said Smith is taller than Jones, what I meant is Smith is at least as tall as Jones. Because I also want to say here Jones is at least as tall as Smith. And continuing, Jones is at least as tall as himself, Jones is at least as tall as Walker, and Walker is at least as tall as Walker. Now notice that the relation R exhibited by the relative heights of these three individuals is not entirely like the numerical relationship, because we have two distinct individuals with that relation holding both ways. In the case of numbers, that could only be the case. Smith at least as tall as Jones, Jones at least as tall as Smith. Now if we're talking about numbers, number X at least as great as Y, Y at least as great as X, then X and Y would have to be identical. It's an important feature of measurement that we don't have that identity of the numerical relationship. We'll talk about that some more, but I want to emphasize that this example 2 displays already a property that generalizes transitivity and connectedness beyond the numerical properties of the numerical relation. It's also easy to construct a counterexample that doesn't have one of these two properties. And let's consider an artificial example. The set A consists of three objects, M, N, and P. And the relation R on that set then consists of M bearing the relation to itself, M holding the relation R to N holding the relation to itself, N holding the relation to P, and P bearing the relation to itself. Now we can ask ourselves, What fails here? Well, first let's check connectedness. If we take any two objects, M, N, and P, taking any two, we have to check that the relation holds at least one way. Well, here M is in relation to N. And here is N in relation to P. Now we ask ourselves, what about P and M? This would require, if we take P and M and P, say, either M holds a relation R to P, or P holds a relation R to M. We look up here, and we don't have any such case. Consequently, the relation fails in connectedness. Now, it's also interesting to ask, what about transitivity? Well, the same example shows a failure in transitivity. We have M, the pair Mn. Notice we exhibit always in these examples the relation holding by writing the pair. So M bears a relation R to M, shown by the pair Mn. And N bears a relation to P. So by transitivity, we should have MP, M bearing the relation to P. So transitivity also fails. So this example is constructed to have both transitivity and connectivity fail. Let's go ahead now to some other properties. Antisymmetry. If A is at least as great as B and B is at least as great as A, then A is identical to B. Now, that's the familiar property referred to earlier that the numerical relation equal to or greater than has. That goes beyond transitivity and connectedness. In fact, our second example, the case of Smith, Jones, and Walker, when we talked about their height, shows that antisymmetry is a property that is independent of transitivity and connectivity. Why is it independent? Well, this example satisfies transitivity and connectivity and doesn't satisfy antisymmetry. It doesn't satisfy antisymmetry just for the reason explained earlier. Smith and Jones are distinct individuals, and yet they have they're judged equivalent in height. And notice that's what we'd expect in measurement. In making numerical measurement, we would expect distinct objects to have the same numerical quality in many cases. For example, the same mass, maybe the same height, the same volume, and so forth. So antisymmetry is a restricting condition, a familiar condition in terms of the number system. We'll see how we make extensive use of it in a moment. Now, a fourth order property that is important but redundant in terms of what we said thus far is a relation being reflexive. A is at least as tall as A. A is at least as heavy as A. In general, air bears a relation greater than, at least as great as, to A. Notice, of course, that the reflexive property, A at least as great as A, is implied by connectedness, by the relation being connected. Because we just take B to be A, and we have here A at least as great as A, or A at least as great as A. But of course that just reduces to A at least as great as A. So connectedness implies a relation being reflexive. We don't need that as a separate property in terms of what we want to consider. Now, it is standard to take the properties we've talked about thus far to define then certain relations satisfying clusters of these properties. The first example is we combined transitivity and connectedness to give us a weak order. In other words, a weak order on a set is a relation that is transitive and connected. Properties 1 and 2 is a relation that is transitive and connected on that set. When we add antisymmetry, so we have 1, 2, and 3, when we add antisymmetry, property 3, then we say that that relation is a simple order. Notice that equal to or greater than on the set of real numbers is an example of a simple order. Of course, a simple order, let's put it this way, every simple order is a weak order, but not conversely. As we've seen by our simple example of height, it's easy to construct weak orders that are not simple orders. These two ordering relations will play a role in almost all of the systems of measurement we will consider. We'll be returning to them again and again. It'll be, in fact, customary in the various qualitative axiom systems considered in later lectures to start with supposing that we have a weak ordering of the objects in question, weak ordered according to some property or cluster of properties. Now, these two order relations occupy a primary role. But let us go on to another relation that is at least as important. To introduce this next relation, we have a fifth property, elementary property, of relations that we want to consider, namely symmetry. A relation on a set is symmetry if for any two objects A and B in the set, if A is at least as great as B, then B is at least as great as A. Or more generally, if A bears a relation R, we might say to B, then B bears a relation R to A. Symmetry, obviously, meaning the relation holds both ways. Now, if we combine symmetry with transitivity and connectedness introduced earlier, we get an equivalence relation. In other words, an equivalence relation has the property of being transitive, connected, and symmetric. It's a generalization of the notion of equality. We can define a relation that is an equivalence relation in terms of our at least as great and relation. And we'll use this wiggly symbol as a familiar symbol for equivalence. Notice how we would read this. A and B are equivalent in mass. A and B are equivalent in height. A and B are equivalent in riding speed, or whatever we may be considering. Notice the definition now. A is equivalent to B if and only if A is at least as great as B and B is at least as great as A. We also correspondingly can define a strict ordering relation. A is strictly greater than B if and only if A is at least as great as B, and it is not the case that B is at least as great as A. Now, familiar properties representing a generalization of the number system are then expressed in the following elementary statement. If the pair A equal to at least as great as the relation at least as great as, if this pair is a weak order, remember a weak order is simply transitive and connected, then the relation we just defined is indeed an equivalence relation. We can prove that. In other words, from the relation holding both ways, it's trivial to prove that if the relation at least as great as is transitive and connected, then this relation is indeed an equivalence relation. That is, in addition to being transitive and connected, it is symmetric. And correspondingly, the strict ordering relation we defined, we can prove, given the properties of the weak order, is transitive and asymmetric on A. That's also easy to prove, and we'll leave those proofs as exercises. Now, I did say one thing about this relation that I want to make explicit. You probably may intuitively have a feeling already for asymmetry. It's the property simply of the strictly greater than relation among numbers, the property of asymmetry. If the relation A is at least as great as B, then it is not the case that B is at least as great as A. Then the relation is asymmetric. And that's a familiar tightening or strengthening of our basic order relation we'll use on many occasions. Now we have, returning to equivalence classes, we're going back and forth between equivalence and strict order. Notice we're going back and forth because we can, in a clear sense, split a weak order into two parts, the equivalent part and the strict order part. We want to define, returning to the equivalence part, the equivalence class of an object A. And I've shown that here by underlining. It's often printed, for example, in boldface. So the equivalence class of A is the set of all objects B such that B is in the given set A and B is equivalent to A. So the terminology equivalence class of A is a natural terminology. And there are some elementary properties that we'll leave for you to prove for yourself. If A is equivalent to B, then the equivalence class of A is identical to the equivalence class of B. In other words, two equivalent objects define the same equivalence class. Notice in stating these properties, I'm of course assuming throughout that we have given a weak order and that the equivalence relation is the one defined earlier for such a weak order. The second property is that if A is strictly greater than B in terms of our strict relation, then the intersection of the equivalence classes of A and B, the intersection is empty. Obviously it holds the other way if B were greater than A. And the third property, that's an important one. If we consider all the equivalence classes, in other words, the set of equivalence classes of the given set A, then that set of equivalence classes partitions A. By partition we mean, of course, the familiar concept of dividing A into a collection of pairwise disjoint subsets whose union exhausts A. So we have a partition of A from this set of equivalence classes. And we have a familiar notation. A familiar notation, A slash the equivalence class symbol, is used for this set of equivalence classes. Now, we've introduced here a lot of terminology. This is going to be the end of it almost for a bit. But it's important to realize this terminology is all elementary. None of it is complicated. The elementary properties are easy to show. It's the kind of thing we get at the beginning. Much of it, for many of you, will be already familiar. One thing we can show, and again we'll leave it as an exercise now, if we consider the set of equivalence classes, that A slash wiggle, as we may want to call it, is that the relation we define on those equivalence classes, so we define that relation in terms of A and B, the equivalence class of A is at least as great as the equivalence class of B, if and only if A is at least as great as B. Well, that relation on the set of equivalence classes, it's easy to show, is a simple order. Notice it is not a weak order. That's incorrect. It's a weak order, but it's more than a weak order. It's a weak order that is also a simple order. In particular, when we go from the relation between the objects up a level to the relation between the equivalence classes, we then get antisymmetry. We get the stronger property of having a simple order. Well, I think with that introduction of concepts and the statement of some properties, we're now ready for our first theorem about ordinal measurement. And this is a theorem that's theorem 1.1, which means it's in chapter 1, theorem 1 of foundations of measurement. I've put it 1.1 because after this theorem, we'll pretty quickly skip over to the more detailed discussion of ordinal measurement in chapter 2. So this theorem, first theorem says, if A is a non-empty and finite set, and if A, the relation at least as great as, is a weak order, then there is a real valued function, phi, defined on A, such that A at least as great as B, if and only if phi of A equal to or greater than phi of B. Notice, of course, phi of A is going to be a real number, and so is phi of B. So the function phi serves as the representing function. Moreover, for the second part of the theorem, we have the uniqueness property. Also, if phi prime is another such real valued function, then there exists a function f that is strictly increasing and is a mapping from the real numbers onto the real numbers, such that for all objects A and A, phi prime of A is equal to f of phi of A. So that f, as this strictly increasing function, represents the degree of uniqueness we get in ordinal measurement. Notice I've just written here the familiar characterization of strictly increasing or monotone function. If the number x is greater than y, for any two such numbers, then f of x is greater than f of y. Required this preservation of the strict ordering for f to be strictly increasing. And it is just that sense of uniqueness of the relation between any two representations, phi and phi prime, being related by this strictly increasing function that gives us a sense of uniqueness. Notice, of course, we would not expect under just ordering relations a stronger sense of uniqueness. In later cases of extensive measurement and so forth, we'll get much tighter uniqueness results. But this is just the right degree of generality and weakness for the case of ordinal measurement. The proof of the theorem for the finite case is elementary and simple. We do want to consider it briefly just because it exhibits one or two properties that will be familiar properties in many of the proofs that we consider later of representation theorems. Although it's certainly fair to say it's the easiest and undoubtedly the most trivial of the. We now turn to a proof of theorem 1.1. First, we need consider only equivalence classes. The reason for that is that if A and B generate identical equivalence classes, then the number assigned to A must be the same as the number assigned to B. 5A is equal to 5B. This is a step we'll take repeatedly in the proofs of representation theorems, is a reduction to the equivalence class structure. That's an obvious and straightforward step. The second and more important part is to construct the representing function phi. And again, we will use here a counting procedure, various modifications of which will be used repeatedly in more complicated proofs. So if we consider the equivalence class of A, we define phi of A. That is the number assigned to A in the following way. It's simply the number of distinct equivalence classes B such that A is at least as great as B. Notice that therefore includes in the counting procedure A itself. So that, for example, if A is the lowest equivalence class in the finite order, then phi of A would be 1. And if we had n equivalence classes and A is at the top of the ordering, then it's clear that phi of A would be n. Having defined phi by this simple counting procedure, starting from the bottom of the ordering, the next thing is to simply show that the if and only if condition holds. That is that, as you remember, A is at least as great as B, if and only if the number assigned to A is at least as great as the number assigned to B. That is, if and only if phi of A is equal to or greater than phi of B. So, for the first part of the if and only if, let's assume that the equivalence class of A is at least as great as the equivalence class of B. Then for every C, if B is at least as great as C, immediately by transitivity we know that A is at least as great as C. Notice that I won't distinguish here between A and its equivalence class or B and its equivalence class in casual talk. Then A is at least as great as C by transitivity. So that means that C is counted for A, that is in the definition of phi of A, whenever it's counted for B, that is for phi of B, and therefore phi of A is at least as great as phi of B. So that by using transitivity we have a proof in that direction. Now let's go the other way. Let's assume that is not the case, that A is at least as great as B. Then by connectivity, B must be at least as great as A. In fact, B must be strictly greater than A. Therefore, there exists a C that is counted in phi of B that is not counted in phi of A. Now, it's obvious what C will do, namely B itself. And so, we have that the number assigned to B is strictly greater than the number assigned to A. And so, we've proved the other half of the if and only if condition. And that completes the proof of the first part of theorem 1.1. The counting approach used there, I repeat, is the simplest case of a procedure we shall use again and again. Now, the proof of the uniqueness is obvious here, and we'll omit it. Well, we won't go through the actual details, which are completely trivial. The severe restriction of theorem 1.1 is, of course, that the set A is finite. In general, we would want to be able to make assertions for ordinal measurement in the cases in which the set A is infinite. You might ask, well, in empirical cases, isn't it the case, indeed, that A will always be finite? It's easy to think of examples where, for the purposes of theory or continuous monitoring of data, etc., it not necessarily is the case that A is finite. So we want to know, is it always true that if we have a weak order, that we can numerically represent it by the set of real numbers and the natural ordering relation on the real numbers? Well, the answer is no. And it's useful to consider a counterexample to show what the difficulty is. And let's now turn to that counterexample. The counterexample is a familiar and classical one, an important example to know its properties. We consider the lexicographical ordering of the plane. We're thinking of the plane as given by Cartesian coordinates. So the set A now is the Cartesian product of the real numbers with themselves, RE cross RE. The ordering relation on the plane, that is the lexicographical ordering, it's called lexicographical because you look at the first coordinate, that dominates the ordering, but if you have equality in the first coordinate, you go to the second coordinate. It's called lexicographical, of course, because we can generalize it to beyond the plane to n dimensions. So the point xy is judged to be at least as great in this lexicographical ordering as x prime y prime, if and only if the first condition, x is strictly greater than x prime, or when that doesn't hold, x is identical to x prime and y is equal to or greater than y prime. Now, it's apparent at once that this weak order is a simple order because we have the antisymmetric property, as we'd expect in this sort of numerical representation of a Cartesian plane. That antisymmetry condition tells us something at once that we will use in our proof of this counterexample, namely that any homomorphism, remember a homomorphism is a function from the set A into the real numbers that preserves the order. Well, this homomorphism, when the relation is a simple order, must also be an isomorphism, that is a 1-1 function. So let's suppose that we have, for this lexicographical ordering of the plane, suppose that we have an isomorphism phi of the ordering into the order structure on the real numbers, that is, into the pair, the set of real numbers, and the natural ordering relation equal to or greater than. Now, for any real number x, let us define phi 1 of x is the numerical value of phi of the pair x1, and phi sub 0 of x, that is the function phi sub 0 we're defining just on x, is the value, the numerical value of phi of the pair x0. Since phi is order preserving, that's by hypothesis of its being an isomorphism, for every x, phi 1 of x is strictly greater than phi sub 0 of x. Why? Because in the lexicographical ordering, the pair x1 is strictly greater than the pair x0. Notice that the first coordinate's the same, and the second coordinate strictly dominates, 1 greater than 0. So we know that phi 1 of x is strictly greater than phi 0 of x for every real number x. Now, for every real number x, we also know immediately that there exists a rational number, let's call it psi of x, that lies in this open interval between phi 1 of x and phi 0 of x. Why? Because it's a familiar property of the real numbers that between any two distinct real numbers, there exists a rational number. So psi x is strictly between phi 1 of x and phi 0 of x. But such a phi defines an impossible mapping. Why is it impossible? Well, first we note that psi is a 1-1 function. Why? Because if x is greater than x prime, it's easy to see that x0 is strictly greater than x prime 1 because we look at the first coordinate now. So that means that psi of x is greater than psi 0 of x is greater than phi 1 of x prime is greater than psi of x prime. Remember, psi x was chosen to be between psi 0 of x and psi 1 of x. So psi x is strictly greater than phi 0 of x, but as we've just seen, phi 0 of x is greater than phi 1 of x prime, which is greater than psi of x prime by the same argument. Psi now, therefore, is a 1-1 function. But that means that psi is a mapping of the real numbers, that is, starting with x, it's a mapping of the real numbers into the rational numbers, because for every real number x, psi of x is a rational number, and psi must be 1-1. But, as we all know, such a mapping is impossible, because that would be a mapping, a 1-1 mapping, from the real numbers to the rationals. But the real numbers are uncountable, the rationals are countable. Such a mapping is absurd, impossible. So we've shown by this classical example of the lexicographical ordering of the plane that not every weak order, or not every simple order, because this is a simple order, not every simple order can be numerically represented in the natural way by the ordering relation equal to or greater than on the set of real numbers. The question to which we now want to turn, when the set A is infinite, as in the case we just considered of the Cartesian plane, what further conditions must be added in order to guarantee a representation? First, we consider the case where the set A is countable. So we turn now to the first theorem of Chapter 2. As usual, let A and the relation at least as great as be a simple order. If A is countable, then there exists a numerical representing function. Notice that with countability, that is, we have a 1-1 mapping of the set A into the positive integers, no further restriction is required in order to get a representation. What this theorem shows is that we can make the first step into the infinite without any additional restrictions. In the finite case, we had no restriction, and in the simplest case of infinite sets, namely the countable infinite sets, we have no additional restrictions. Of course, our counterexample to simple orders in general being numerically represented, the lexicographical ordering of the plane, did not satisfy this countability condition. The proof for the countable case that we do have a representation of ordinal measurement was given in the end of the 19th century by the German mathematician Georg Cantor, the one also responsible for much of the work on infinite sets and transfinite numbers. Let's look at the proof of this because it is a natural generalization of the proof for the finite case. First, let psi be the mapping of the set A into the positive integers. In other words, let psi be a function which shows that A is countable. We use the notation then for an element A of the set A sub n is the nth element under the mapping psi. That is, psi of A is equal to n. And our problem now is to construct our representing function phi. Remember, in the finite case, we simply used a very simple counting procedure. Now here we don't know that we even have a first element. The countable ordering could be such that there is no first element and no last element. For example, the rationals are countable and have no first element or last element, or the full set of integers is countable but has no first element or last element under the standard ordering. What we must do then is, with a little more care, define by induction the function phi. So what we now want to consider is the inductive definition of phi. Phi of A1, the first step in the induction, is equal to 0. And now we must consider three different cases for the definition of A n plus 1, that is, the number assigned to the n plus first element under the countable function psi of the set A sub n plus 1. First, we have a very easy situation if for all k equal to or less than n, that is, for A sub k with 1 equal to or less than k equal to or less than n, we have that A n plus 1 is greater in the ordering than A sub k. We simply assign A sub n plus 1 the number n, as shown here. The corresponding case when A n plus 1 is below all the elements assigned numbers thus far is also simple. In that case, we just assign the number phi A n plus 1 is just minus n. Notice that is a little crude. We could have some mixing there, but that certainly works. N in the first case, minus n in the second case. The complicated situation is the third case, when A n plus 1 is neither above all the elements previously given numerical assignments or below all the elements. Well, from the finiteness up to this element, n plus 1, we know there must exist elements I and j with 1 equal to or less ij equal to or less than n, such that ai in the ordering, the ordinal ordering we're considering, ai is strictly greater than a n plus 1, which itself is strictly greater than aj. And for all k, these elements get as close as possible to a n plus 1. That is, either a sub k is equal to or greater than ai, that is, it's over here, or for every k, it's over here. A sub j equal to or greater than a sub k. In that case, it should be obvious we just look at the numerical weighting, the numerical assignment to a sub I, the numerical assignment to a sub j, and take the midpoint. That is, phi of a n plus 1 is just 1/2 of phi ai plus phi aj. And that takes care, as is easy to show, of the three possible cases we could encounter in the inductive definition of the numerical value of a sub n plus 1. Now, that inductive definition doesn't prove that we have the proper order-preserving properties for phi, but that also proceeds by induction. We'll omit that proof, leave it as an exercise, but it's straightforward once we have in front of us this inductive definition of phi. We now want to ask ourselves, what about sets that are not countable but infinite, uncountable sets? Well, as our example of the lexicographical ordering of the plane shows, that even if the set has the cardinality of the continuum, that is, there is a 1-1 mapping from the plane into the real numbers, but not one that preserves order, we have a problem. We can't not in general have an order-preserving representation. But if we think about examples we've been discussing, it's clear that there is a natural property of the real numbers that we should be able to generalize. Namely, the kind of property exemplified by the rational numbers. Namely, we have the countable set of rational numbers being order dense in the real numbers. Remember, that's what we used as a method of argument to show that we couldn't have, for the lexicographical mapping of the lexicographical ordering of the plane, a proper mapping into the real numbers, preserving order. If we now impose that order-dense property of the rationals, we will get a necessary and sufficient condition for numerical representation of the order. And let's look at the definition of order-dense in a general way. So we start, as usual, with our standard simple order, and B is a subset of the given set A. Then B is said to be order-dense in the set A if and only if we take any two elements A and C in A, with A strictly greater than C under the ordering, there must exist a B in B that lies in between. That is, such that A at least as great as B, at least as great as C. Notice that just generalizes the familiar property of the real numbers. If we take, thinking now of the real numbers, if we take any two distinct real numbers, say x greater than y, we can always find a real number, a rational number in between, as in the case of B here. So this property of order density is just the natural extension of an order property we find in the real numbers by considering the rationals to the general case. And we use now that condition of order density and the condition of countability to state the appropriate representation theorem for the general case. And that is theorem 2 of chapter 2. If we have a simple order, then the following are equivalent. There is a finite or countable order dense subset of A, or condition 2, there exists an isomorphism from the simple order into the real numbers under the natural numerical ordering. Notice we would have got the ordinary representation theorem by saying if condition 1, then 2. But actually condition 1 is both necessary and sufficient, because if we have 2, it also implies 1, as is shown by this equivalence. So we have, in that sense, the representation conditions are strong conditions here. They're both necessary and sufficient. Now, we want to examine the proof of this theorem without considering all of the details, because it is a classical theorem, also proved by Cantor in essence, though a little bit incompletely, and it is really the general theorem on ordinal measurement. So we need to define a concept we've used implicitly already, and that is the notion of a gap. We say that a pair A prime is a gap if we have the property that for every B in A, B is at least as great as A prime, or A is at least as great as B. It follows from that, of course, that we also want that A is strictly less than A prime. We can put here A prime strictly greater than A. And in terms of that now, we can define, we can characterize the following lemma that will be useful. Let A starred be the set of all endpoints of gaps. A and A prime are, of course, endpoints of gaps. The set A starred under the hypothesis of theorem 2 is finite or countable. That's what we want to prove. Now, the proof, of course, breaks into two parts. We need to prove that the set of endpoints is finite or countable under condition 1, that there exists a finite or countable order-dense subset of A, and then under condition 2, that there is an isomorphism. We'll just really consider condition 1. The argument for condition 2 is like the familiar argument about the rationals. So suppose that condition 1 of theorem 2 holds, that is, that we have a finite or countable order dense subset of A. And consider a gap, A prime. Well, by the definition of being order dense, either A has to be in B, that is the order dense subset of A, or A prime, little a prime, has to be in B, because there's nothing in between the two, so that, and considering any two elements, one of them would have to be in B. Let A sub 1 starred be the upper endpoints of gaps, and A sub 2 starred the lower endpoints. What we want to show is, first, that A sub 1 star, that is the set of upper endpoints, minus the set B, is finite or countable. Now, why is that so? Well, the argument is easy. An element of A1 starred is either in B, by the argument just given that A is in B, or A prime is in B, and if it's not, to show that it's finite or countable, we establish the correspondence to its lower endpoint. Because if the upper endpoint is not in B, by what we just said, the lower endpoint must be. And so we have the appropriate correspondence. That establishes that A1 starred minus B is finite or countable. By precisely the same argument, it's obviously symmetric, A2 starred minus B is finite or countable. That's the set of lower endpoints. But we now use two familiar facts from elementary set theory. First, the intersection with a finite or countable set is itself finite or countable set, no matter what the intersecting set is. So A starred intersection B is finite or countable because B is finite or countable. And secondly, the union of finite or countable sets, the finite unions, must be also finite or countable. And A starred is the union of three sets that are finite or countable. A1 starred minus B, union A2 starred minus B, union A starred intersection B. It's easy to see that that's an exact representation of A starred. And so that proves that A starred under condition 1 of theorem 2 is finite or countable. And as said already, there's a familiar argument we'll not go through in the case condition 2 of theorem 2 is the one under consideration. With this lemma available, we are now in a position to go directly to the proof of theorem 2. So we're now ready for the main proof of theorem 2. First, some definitions. As usual, let B be the order dense countable subset of A that we're assuming in the hypothesis of the theorem, that is in the part 1. Secondly, let A starred be the set of endpoints of gaps. And we'll include, if the ordering happens to have it, the first or last elements. Of course, it's not necessary, and there may not be first and last elements, but if they are in the ordering, include them in A starred. By the lemma, the set B starred, which is B union A starred, is finite or countable. We know why, again, because B is by hypothesis countable or finite, and so by lemma 1 is A starred. And the union of two such sets is again finite or countable. Under this countability hypothesis, or finite hypothesis, as the case may be, by theorem 1.1, the first one we proved for the finite case, or theorem 1 of chapter 2 for the countable case, we know at once that there exists an order-preserving numerical function representing function phi prime from B starred to the real numbers. We now want to use that phi prime to construct the full representing function phi. As before, our proof proceeds in two steps. First, we construct phi, and then we prove that it has the desired properties. So for the construction of phi, we now go one step beyond theorem 1 of chapter 2. Remember, In the first theorem about finite sets, we had a very simple counting definition of phi. In the countable case, we had a relatively simple inductive definition of phi. Now, for the general case, we must do something a little more complicated. We define for an element A, in A, phi of A as the least upper bound of the set of all numbers phi prime of B, such that B is in B starred and A is at least as great as B. Notice in this definition, we make the definition of phi depend on phi prime and on the countable set B starred. Now we have the usual problems about that. We have to show that the least upper bound of this set exists. And there are two problems in showing that. First, that the set is non-empty, and second, that it's bounded from above. Well, if A is in B starred, there's no problem at all about phi of A existing. The real question about existence, if A is not in B starred. If it isn't in B starred, then we know that there exists A1 and A2, such that A1 is strictly greater than A, strictly greater than A2. It's easy to make that argument to show that there is such an A1 and A2 from the properties of B starred and the assumptions about the order. By order density, then, we have A1 at least as great as B1, strictly greater than A, strictly greater than B2, at least as great as A2. So the set phi prime of A, given this condition, B and B starred and A at least as great as B, is non-empty. Why? Because in terms of the inequality I just wrote down here, phi prime of B2, that's right here, is in phi of A. Since that B in B starred is no greater than A, and so by definition it must be phi prime of B, in that case B2, must be in the set as defined here. So that proves the set's non-empty. But on the other hand, by considering B1, we can also prove that the set is bounded from above, because B1 is strictly greater than A, and therefore phi prime of B1 bounds the set from above, and since the set is non-empty and bounded from above by the standard theorem in elementary real analysis, the least upper bound of the set exists. And so we know from that that the function phi is well defined for all elements in the set A. Now the second part of the proof of the main theorem is to prove that phi is order preserving. Suppose A prime is strictly greater than A in the given ordinal setup that we start from, that the ordering of the set cap A. Then it's easy to show that we must have elements B, B starred, B, B prime in B starred, such that A prime is equal to or greater than B prime, greater than B, at least as great as A. And from the definition of phi, we know at once that phi of A prime is at least as great as phi as B prime, because remember the definition of the set and the least upper bound, and which is strictly greater than B from this relation, since these are elements of B starred, equal to or greater than phi of A. Well, that shows that phi of A prime is equal to or greater than phi of A, which is the desired order-preserving property. The inference now the other way is similarly easy. Suppose phi is an isomorphism of the simple order into the real numbers under the natural ordering. Let J equal the set of pairs of rational numbers, R prime, such that there exists an A and A with R prime greater than phi of A greater than R. For each R prime, that is for each pair in J, we choose exactly one A and A such that condition 1 holds. Now notice in general there will be many such A's, but we now pick exactly one for each pair. Let B1 be this set of elements. Then because of this relation to these pairs of rational numbers, J is a countable set, B1 is finite or countable, because J is at most countable. That is, it's either finite or countable. B1 must be finite or countable, because there's this 1-1 relation between J and B1. Now, it's easy to show. That's the first part of B1. Remember, we're showing, under the hypothesis we're going now, that having phi is an isomorphism, there is such a finite or countable set that is order dense. And given B1 and its construction, it's an easy argument to show that B1 is also order dense. The only problem is to consider slightly carefully the case of gaps. And with that, we conclude the sketch of Theorem 2, the proof of it. The complete details of the proof are given in Chapter 2 of Foundations of Measurement. Now, I have not stated here the theorem on the uniqueness of representation in the case of for general sets A, because that statement is exactly the same as we considered for finite sets. Namely, we get a strictly increasing function as a uniqueness condition. And again, the proof is straightforward and trivial and will be omitted. With this remark about the uniqueness theorem, and with the proof of Theorem 2, we conclude our treatment of ordinal measurement.